Welcome all to our 44th Van Horn lecture series. It's a great pleasure to see you all here, and it's a particularly great pleasure to welcome this year's Van Horn lecturer, Professor Schuh from the Department of Materials Science and Engineering at MIT. I will first give you a brief overview of the background of this lecture series, and then Professor Lewandowski will introduce Professor Schuh for you. So this is the Van Horn lecture series, and the name Van Horn is very well known on this campus. And it actually is the last name of a number of interesting people. At the beginning is Frank Van Horn, who used to be a professor of mineralogy and geology at around 1900. And he's actually at the founding root of what you see here today as our Department of Materials Science and Engineering. He traveled the world collecting rocks, and some of what he collected can be seen in the Cleveland Museum of Arts as a substantial part of their exhibition. He also was a great sportsman, which is why the field in front of the Wield Center is known as the Van Horn Field. He started what we do here by donating funds, the Van Horn funds, scholarship funds, and that was a donation he made together with his wife. And they had a son, Kent Van Horn, who was actually a metallurgist and a Case alum. He graduated in 1926 and actually received the gold medal from the Case Alumni Association in 1970. He moved on for doctoral studies to a city that is nearly as beautiful as Cleveland. Can you guess? Heidelberg, Germany. And he also learned German. He then moved on to an industrial career. He was leading the laboratory of Alcoa in Cleveland for many years, and then moved on to become the senior executive vice president of Alcoa in a small town that's called New Kensington near Pittsburgh. And he significantly increased the Van Horn scholarship funds. And that is the basis for our Van Horn lecture series. How do I know all of that? Well, I talked to his son, Carl Van Horn, who visited us here in his 70s, mid-70s last year. And he also started out as an engineer at Yale, but then something must have happened. He moved to Cambridge and studied politics and philosophy and economy. And he then became the chairman of Arlington Financial Company in London. He is currently administering or executing the family's funds, and that is helpful for us, again, for this event. So the Van Horn lecture series has a mechanism that we've repeated for many years now, which is that our faculty of this department, scans the field of material science for eminent scholars that have a broad range of interests, who have had significant impact on the field, who are likely to be able to give a dynamic presentation for us about what they do, and who are likely to be able to communicate well with students. And I believe that Professor Schuh has all of these attributes perfectly fulfilled. And we then vote on this year's or next year's Van Horn lecturer and invite that person for 1 week. And during this week, we will always have 3 lectures. And the time in between is spent by the Van Horn lecturer discussing about our research, and that discussion is supposed to focus on the students and postdoctoral researchers. That is the goal of this event. And I guess that's all I have to say at this moment, except there is one organizational point I want to make you aware of. We would have normally have had the lectures every day at the same time in the same location. But now tomorrow we have another important event, which is our chairing procedure. And because of that, we had to move up tomorrow's Van Horn lecture in time. And we will have our reception for it already at 3 o'clock in the undergraduate lounge in the 3rd floor. And at 3:20, we will move over to Nord Hall to have the lecture starting at 3:30 in Nord 356. That's the big lecture hall in the bottom with the glass walls that you see when you walk into Nord Hall. So please remember that. If you come here tomorrow at 4 o'clock, this place will be deserted. So I hand over to Professor Lewandowski to introduce Professor Schuh.
Thank you, Professor Ernst. Again, this is quite a pleasure. This is quite a unique activity in the department that's been going on for quite some time, and the ability to meet with students and faculty is really something that I'm not aware of anywhere else around the country. So we were able to enjoy a nice dinner last night at Washington Place, and a number of the faculty at my table were remarking how much we like academic life, because every year there's a crop of new students. And it seems like the students get younger and younger every year, at least to us. Of course, that's not true. However, our Van Horn speaker this year is younger than any of the other Van Horn speakers that we've ever had. That started back with Joe Burke. And I won't get into the details of this, but our Van Horn speaker wasn't even born yet. And so we checked his birth certificate. I won't share that with you. But some of us have been watching very carefully what he's been eating at dinner and throughout the day, and we're going to try to implement this into our diet. And you can watch what happens to us as time goes on. So how did this happen? So let me give you a little of the background of Professor Schuh, who wasn't always that, obviously. He got his bachelor's degree in materials at the University of Illinois, Urbana-Champaign. And then he went to Northwestern and got his PhD in 2001 with David Dunan, who a number of us know, and he was a National Defense Science and Engineering Fellow at that time. And interestingly, some of his earliest papers were on TiAl, which is a material that's quite often used now in jet engines and continues to evolve, and there's work going on in the department on that. But in addition to that, he did work on Ti-64, which is a workhorse titanium alloy, in addition to some composites. And there were some interesting papers on what was called transformation mismatch plasticity, which was looking at processing and structure evolution using some phase transformations that might occur during the process. And not only was that used on metals, but there was also apparently some papers on ice containing silica particles. So very unique. So then he did a postdoc. In 2001-2002 at the Lawrence Livermore National Lab as a Ernest O. Lawrence postdoc, which is a very prestigious postdoc, and he worked with T.G. Neate, that a number of us also know. And this was in areas of metallic glasses and starting some work on nanocrystalline materials. And there was a series of unique papers that came out from that early work. Nanoindentation, the rate dependence of flow, where some very unique and a little bit initially controversial details and aspects were put forward. Now, I was on sabbatical in Cambridge roughly around that time, working with Lindsay Greer, who was our Van Horn speaker in 2010. And so Lindsay shows me some of these papers and says, this looks kind of interesting, should we do something? And I think I told him, I think it's too late. Chris is onto something, and he ran with it. And there are a number of very nice papers on the modeling of flow in metallic glasses that extended down to the atomistic level. He also looked at homogeneous versus localized flow in metallic glasses and new regimes of homogeneous flow at high temperatures, and extended the kind of the famous Spaten mop for deformation map of those materials. That work was then extended to bulk metallic glass composites to also include their plasticity. But along that same time, there were some early papers on nanocrystalline nickel as well as alloying effects. So now he goes to MIT in 2002 as an assistant professor and rapidly rises through the ranks to full prof in 2011. Along the way, as you might imagine, he's gotten a number of Young Investigator Awards, and in 2004 he got 3, one from NSF Career, NSF PCASE, and an ONR Young Investigator to fund some of that early work at MIT. He also got the TMS, Material Society, Robert Lansing Hardy Medal, which is given for exceptional promise for a successful career. And that year also at MIT, they awarded him his current chaired professorship, which I may pronounce incorrectly, the Danai and Vasilis Salapatas Chair in Metallurgy. So our paths have crossed at a number of international conferences, mostly on metallic glasses, in China, in Tennessee, and a number of other places, where Chris gave a number of very succinct, detailed keynote and invited talks on some of the things that I've already described. In addition to that, in 2007, he was the lead author on a review paper in ActaMet that's now received over 1,400 citations on metallic glasses. And those other works that I described are equally in the multiple hundreds at this point. So consistent with that, he's also won a number of paper awards with his collaborators and advisees, ASM, TMS, and 2 from MRS. Now, in addition to that, since this is a student focus, all of this stuff was done without neglecting his teaching and educational activities. And so in 2011, he won the SAE Ralph Ketor Award, which is for educational aspects. And that same year at MIT, he became the McVicker Faculty Fellow, which honors MIT's best undergraduate teachers and mentors. And there's a limit to the number of those, I guess, that exist at MIT. So he was also rewarded that year with the department chairmanship in 2011, and he heads, obviously, the top-ranked department that a number of us acknowledge. Other major service activities include acting as coordinating editor for the ACTA family of journals. So that's Acta Materialia, Scripta Materialia, and Acto Biomaterialia. More recent awards from TMS include a Fellow Award in 2015. The significance of that is there's only 100 living fellows that exist at any one time for those. So the work on nanocrystalline metals also started early. It's equally well cited, and that's a continuing thread that you're going to hear through the next 3 lectures, including various entrepreneurial activities that will be covered in tomorrow's talk. So if I return to my original question of how he became the Van Horn speaker at such a young age, it's clear to me, and you'll see very shortly, that he's earned this by extending the work that he did in his PhD, but to much different diverse systems, using different techniques that include both modeling as well as processing and structure evolution and properties. And both junior as well as senior colleagues are now referring to that work. Just a couple of weeks ago we had Carl Koch here, and he cited some of Chris's work that you're going to hear about later. So with that, I want to introduce his talk on harder, cheaper, greener, the material science of nanostructured metal coatings. Great.
Well, that's easily the most embarrassing introduction that I've ever been subject to. So, John, thank you so much for that. I want to say that it is really an incredible honor, real pleasure for me to be here. When Frank gave me a call some months ago to let me know that I had been nominated and selected for this, it was really humbling and stunning. And looking over the list of previous Van Horn lecturers has not been good for my nerves, to be totally honest. So I'm not thrilled to know that I'm the youngest one. That doesn't help. So, but anyway, I really do feel like this is a very special thing. I have never seen anything like this at another university, and so thank you for letting me be part of it. So Another very interesting thing is that if you're going to give 3 seminars, it's challenging to come up with a theme that you can weave through 3 consecutive seminars. And so what I'm going to do with the time that you've given me over the next 3 days is tell you a story in almost chronological order from the time I arrived at MIT until today on a thread that I've been working on continuously and trying to get smarter about that entire time. And it's on the topic of nanostructured materials. And because I sit in a department of materials science and engineering, what I really want to do is talk about how you can do both of those things and how you can try to connect those things with your work and do new science, new scientific ideas that connect to engineering application. So if I can do that over the next 3 days, then I will be delighted with the opportunity to do it. Frank also told me that there's a big burden that because for 3 days I have to attract students to come to these lectures, and of course so I have to do something to make it exciting, and I think he said it's got to be Bafo Sacco, super exciting and lots of sex appeal. I think those were your exact words if I remember correctly. So I went ahead and I wrote titles that sort of have a lot of sex appeal in them. I made sure I got some nano in there and coatings, and these kind of evoke ideas about maybe we're going to be going to Mars or entrepreneurship. So I thought I would start this first talk by going ahead and just dispelling completely any notion that there will be sex appeal in this talk. What I'm going to talk about is stuff like this, okay? So I'm a metallurgist, I'm a structural metallurgist, and I'm interested in problems that can touch a large cross-section of humanity. And so I tend to be interested in things that don't have intrinsic sex appeal. And so on this theme, I walked into Home Depot and I'm looking around for the least sexy component that you can imagine, and this is what I came up with, right? So this is emblematic of a lot of parts that I care about that are incredibly useful, incredibly prevalent, incredibly important to our society. This thing here has a lot of very important properties to it, not the least of which is that it is affordable. This cost me $1.95 or something at Home Depot, right? And this thing has a lot of function in $1.95. It's made out of a material that is, inexpensive and highly formable. It's going to be subjected to conditions where it's going to see corrosion, it's going to see wear, it's going to see a gamut of threats, right? And yet we still have to do it for $1.95. So if you're interested in structural materials, and if you're interested in coatings, this is why. It's because coatings are a surface functionalization that adds a ton of value, right? So I can take this thing that's $1.95, I can render a coating onto it, I can add function to it, I can make it more wear resistant, more corrosion resistant, and I can do that in a way that adds a lot of value. And if you're interested in metal coatings, and if you're interested in high volume metal coatings that do things like wear and corrosion resistance and appearance, there's one technology that is just the dominant one out there. And so I chose early on in my career to focus on electrodeposition as a means of rendering high value metal. Electrodeposition, you all know it, you probably all did it in high school, right? It's an aqueous solution with dissolved metal ions from salt. You render your component, the cathode, in the electrochemical reaction and flowing some current through there, you can put down nearly conformal coatings over very complicated shapes, and you can add really a lot of value to the component in doing that. So, I'm just starting at MIT. I'm interested in this kind of problem. I like mechanical metallurgy, I like hardness, I like corrosion resistance. If you're interested in all these things on this page, there's one obvious place to start, and that is the domain of what we call hard chromium coatings, all right? So you all know what chromium coatings are because they are everywhere all around us. In fact, the furniture in this room is coated with chromium because it is the dominant high-strength electroplated coating that's available. We use it on everything. So we use it on processing equipment, we use it on things that are under the hood, both literally and figuratively. And of course, when you look around and you see it around you, you use it every day because it's used in decorative applications, because it's hard and it's corrosion resistant, so it doesn't scratch and look smutty, and so it is also then shiny. And so you can use it, if you took a shower today, I hope you took a shower today, then it's on every faucetry item in the world, right? And of course, if you drive around in a pimpmobile, as so many of you in Cleveland do, I understand that in the world of pimpmobiles, the more chrome you have, the higher is your stature, right? So you know a lot about it. And did you ever think you'd hear a scientific talk with Pimpmobile in it? No, probably not. So I got that going. All right, so we use this stuff everywhere. This is really a prevalent metallurgical product, okay? And we use it to the tune of $20 billion a year. That's the value just in the metal coating, not in all the stuff we put it on. If you sum up the value of all the stuff that we put it onto, it gets almost to $1 trillion of stuff, right? So this is a huge, huge industry. It's critically important, and we use it everywhere. We use it everywhere because of its amazing properties, right? So it is hard. It is 8 gigapascals hardness, which means that it has great wear properties. And of course, because it is chrome and it has a very good tenacious oxide layer, it's good for corrosion and therefore stays shiny. However, it is not all smiles with chromium. And if you circulate in the industry that renders chromium coatings, you will find a lot of complaints. It's not an efficient process. It doesn't cover things very uniformly. It's sort of inefficient. But in the modern world, there's a bigger problem associated with chromium coatings, and that is that the precursor chemistry that we use to render those coatings is based on hexavalent chromium ions in solution. And I'm getting a lot of blank looks from this room about hexavalent chromium. So if you don't know what hexavalent chromium is, and you would like to dip your toe in and access the literature and learn a little bit about it, I would recommend as a starting point the 1999 classic contribution to the literature from Julia Roberts. This is the movie Erin Brockovich, where you can hear her whine for 2 hours about hexavalent chromium and its societal ills, right? Because this chemical is toxic, it is carcinogenic, and it is, in fact, quite a serious threat to worker safety and to the environment. And it is, a perennial entry on the list of hazards that humanity is trying to regulate out of existence. Here's an example of that. This is from OSHA. So the biggest threat of chromium is to the worker in these plants that are rendering the coatings because they're exposed to the airborne evaporant that contains hexavalent chromium ions. And so here's the history. I guess before 1971, the environment was discovered around 1971, I guess. So we didn't regulate this stuff, but then suddenly we do regulate this stuff. And a factor of 10 was implemented about a decade ago, and there's constant suit to continue lowering that exposure limit. So when I arrived at MIT 15 years ago, to me, this is what material science is really all about. I have here a material that is really useful for humanity, but it has a lot of baggage attached to it. And so to me, this is one of the things material scientists should do. We should dig in deep, we should look at this kind of problem, and we should figure out if we can't solve it using material science. And so what I would like to talk about today is our efforts to develop alternatives to chromium coatings. So let's start at the beginning. And at the risk of, making this too babyish, I'm going to start with a little diagnostic work. I'm going to talk about the structure of chrome. Why is chrome so hard? Well, if you cut open chrome, this is from the literature. This is Huang, 2005. They cut this open and they did some TEM. And what you're looking at here is, conventional polycrystalline structure, right? So it is polycrystalline. If you note the scale bar, you'll note that these grains are very, very fine. So in fact, you might call this a nanocrystalline solid. And I would argue that hexavalent chromium is probably the oldest nanomaterial in use. We've been using it since the 30s. You use it every day. It's a nanostructured material. So there's nothing new, right? Nanotechnology is baked into your life every day in chromium. And in fact, that is why it's a hard coating, because that structure gives it its hardness. So Metallurgy 101, here's the Hall-Petch relationship. If I take the grain size, from the micron scale down to that scale that we just saw in that micrograph, we get hardness out of it. And in fact, these are the data for chromium, for BCC metallic chromium. And sure enough, it turns out that when you electroplate chromium from a hexavalent bath, it's not by design, it's just the way it happens. You deposit this stuff, and it has this grain size, and therefore it is hard. Okay? So that's the basic recipe. If you want to make a hard coating that's going to be able to replace chrome, you're going to make it nanocrystalline to cash in on the same mechanism. So we have here now a fairly obvious recipe. We want to put this stuff on top of substrates that sit down here. We now know that a nanocrystalline structure, thanks to the Hall-Petch effect, can sort of get us up above that band. The recipe is fairly obvious, right? So why don't we just take this recipe that we know and love and just do it again and don't use chrome, right? Let's use some other metal. And in fact, this is an obvious recipe. And if we did that, it would be a step forward, assuming that the metal ions that we're putting in substitution are environmentally more benign. So that's the basic premise. And it is an obvious idea, and people have in fact been working on this for decades. Okay? So in the 90s, in fact, there was a lot of activity where people were diddling with electrodeposition baths and trying to manipulate grain size so as to make nanocrystalline coatings out of other metals. And here's an example. This is now nickel. Nickel is also a $20 billion chemical electroplating industry. We know how to electroplate nickel. Electroplated nickel, however, tends to fall in the range that I'm showing here in terms of its grain size. So it gets below a micron and it gets above a micron, but it's on this part of the Hall-Petch curve that is not nearly strong enough to really cash in and use it as a hard coating. And so the question is, how do we get it there? And like I said, in the 90s, this was a hot topic. And so people were fiddling with the chemistry. They were adding all kinds of additives to promote nucleation and therefore get more grains as they were growing the coatings. Very heavily trodden territory and very successful. In fact, all of these data are from 1993 and earlier. So back in the early 90s, humankind already knew how to electroplate from supermicron down to about 10 nanometer grain sizes. And in fact, that is hard enough that you can sort of envision putting this on top of that and you're good to go. And these are beautiful materials, right? So here is a typical electroplated nickel. This is from my lab when I first got to MIT. The purity is quite high. It's 3 nines or better. It's full density. It's very fine grains, and it's very strong. And so, why am I still talking about this, right? Like, if in the 90s we knew how to do all this, why is this a topic that I'm talking about today? Isn't this a nanotech success story? And the answer turns out to be no. The answer turns out to be that this material, although it is a very nice laboratory experiment, it's a very nice piece of science, it is not a deployable technology. And there's a serious problem here. And in fact, it's the oldest problem in all of material science. It is that this is an unstable structure, and those grains are going to grow, right? So, J. Willard Gibbs, your hero and mine, father of us all, right? Chemical thermodynamics. J. Willard Gibbs, back in the Victorian era, had nanotechnology all figured out, at least as far as this problem is concerned. You know, he told us that if we add interfacial area to a material, if we add grain boundaries to a material, those things have a positive energy penalty, akin to a surface energy. And so as we push the grain size down, it turns out to be a parabolic walk up an energy hill in terms of having more internal energy in the material. So although we may diddle with our electroplating bath and figure out a way to sort of trick nature and put a boulder on the side of this hill, all we have done is put a boulder on the side of this hill. And it is not in a stable configuration, and so we should expect that it's going to slide down to the right. And it is right around when I got to MIT that the field was really figuring out just how crippling grain growth is in these nanocrystalline materials. This is from 2002 from a Canadian group. This is Hibbert et al. And they did the following very nice experiment. They electroplated nickel right at the apex here. Beautiful, 10 nanometer material, very, very hard. And then they did some thermal exposure to it. For example, they heated to 400 degrees, right? A nice low temperature for nickel. And they watched how the nanostructure turned into a microscale structure in a matter of seconds, right? Seconds. Seconds of exposure. So if you ever wanted to braze this material or join it or heat treat it or do anything to it, you've got a very small thermal budget if you're going to go to 400C. And of course, if you wait for a week, you can literally slide right off the end of this chart, right? So in seconds, we're down here, and in days, we're down here. And now it's soft as butter, and you can scratch it with your fingernail. So I know what you're thinking. You're thinking, my Pimpmobile rarely sees 400 degrees C. I'm in Cleveland. It's pretty cold here. It turns out that this problem, it's thermally activated. It's grain growth. If you cool things down, it happens more slowly, but it still happens. And one of the first things I did at MIT is I repeated this experiment, but we did it at ambient temperature. And what we found is that we could produce this material, and if we would wait about 3 months, we would slide down to here. And if we waited a year, we were sliding down to here. A small change in grain size is a huge loss in hardness. And so this grain growth, even at room temperature, is a serious problem. So these are not deployable. So this recipe, although kind of cute and simple on the surface, requires some new ideas. And that's what I want to focus on for the rest of this talk and indeed the rest of the week. And the thing that we need to make this deployable is structural stability.
Chris, why doesn't this apply to the chromium?
That's a great question. So chromium, there are at least two answers. One is that chromium, being BCC, has a Hall-Petch slope that's shifted, so the grains are larger. They're about 100 nanometers vis-a-vis 10 that you need in nickel to get the same hardness. Secondly, chromium, as it turns out, when you deposit it, has a whole bunch of oxygen in it, which stabilizes it. So we are going to work on trying to stabilize nanoscale structures. And so now we're going to go back to the root of this problem. And like I said, this is the oldest problem in the book for material science, grain growth, right? Slowing down grain growth, stopping grain growth. This is something that people have done in 100 contexts before. The thing that I would point out is that, I'm going to view this problem as a thermodynamic problem. I already told you my hero is Gibbs. Here's a picture of me with Gibbs. The point here is that if you look at all the literature and how we address grain growth, we almost always are playing a kinetic trick, right? Material scientists usually are trying to slow down the motion of grain boundaries. They put in things that affect solute drag. They'll put in pinning precipitates. These are all, in essence, sort of kinetic tricks to slow it down. I guess the argument I would make is, there's probably something we can do on the thermodynamic side, and we might need to in light of just how steep this curve is when you get down to the nanoscale. Merely slowing it down might not be good enough. And so maybe we should try to address the fundamental problem, which is the shape of this energy landscape. And so that's what I'm going to do. So here's the way we're going to do it. And in fact, this is directly from J. Willard Gibbs himself, who also wrote down this equation here, which is the same exact equation. So what I'll emphasize here is that the first term, the leading term, is the same one that we had here. That's the grain boundary energy of pure nickel, if you will. And that is our enemy. The second term that we're adding here is what happens if you have an alloy system and you start adding second components, right? So what we're going to do now is we're going to add an alloying element, and we're going to add an alloying element that is intended to segregate to the grain boundaries, preferentially decorate them. So it's going to have a free energy of segregation that is positive. It's going to decorate those interfaces with a specific excess. And the beauty of this is that this equation, in other contexts, we call this the surfactant equation. You're going to add an alloying element that will go to the surface and lower its energy. And in fact, this term here, if you plot it out in red, it looks schematically something like this. So now we are actively tailoring the energy landscape of the interface. And in principle, if we put these things together and we map it out, you can get a free energy landscape that has a minimum in it at a finite grain size. So grain growth is no longer an unbounded slide to the right. There can be a valley here. So here's my cheesy boulder sliding, and that's as far as it's going to slide. Okay? So, tantalizing idea, a thermodynamically preferred grain size. Step one, in my group at MIT, before my students really do anything, they have to go bend equations, all right? So you got to go think it through and do the best you can to sort of model out what you're going to do in the lab. So the first thing we're going to do is we're going to take this equation here. This is sort of a schematic equation. It's very simple. And what we're going to do is we're going to modify it to try to apply it to metallurgical alloy thermodynamics. So the way we do this is we start with the regular solution model. Have you all seen the regular solution model? Please nod. Okay, good. So we start with the regular solution model, and what we do is we add grain boundaries to it, and we just sort of turn the crank and derive out the regular solution model if there were grain boundaries present, and we write down this modified form of that term right there for a binary alloy, simple pairwise interactions, and I'll wait a second while you write this down. What I want to point out here, looks very elaborate and complicated, but everything in this equation is actually something that we know or which is knowable. So first of all, the leading term here, the blue term, is still there, right? That's the energy of the grain boundary of pure nickel. And then we decrement off all this other stuff, which all just pertains to the segregation to the interface. And what I'll point out here is that it incorporates a bunch of things that we know what they are. It incorporates interaction parameters, so heats of mixing, if you will, in the bulk and in the grain boundary. And if those are different, that is what drives segregation. And the way it boils down is everything in this equation is something we can know if we but know those things. So if we know the heats of mixing in the boundary and in the bulk, then we can calibrate this model. Now, one of the nice things about working on the nanoscale is that you can now go in the computer and try to calibrate those things in as quantitative a way as possible. And so this is an example of the kind of simulation we do in my group when we're trying to survey a whole lot of grain boundaries at once and explore their energetics. So we go in the lab and we build this thing in the computer. So this is a structure that we would love to make in the lab if we knew how. The grain boundaries here are highlighted in red just so you can see them. But every atom here is nickel. And they're all talking to each other through multi-body potentials. This happens to be Finney-Sinclair multi-body potentials. Now what you can do with a structure like this is you can start alloying it and looking to see if various alloying elements segregate to the boundaries or not and whether they lower the energy of the boundaries or not. Tomorrow and on Thursday, I'm going to tell you more about how we choose which atoms we put in, right? How do we select the atoms? How do we find a surfactant for grain boundaries? For today, I'm just going to tell you the lucky answer. The lucky answer for nickel turns out to be tungsten, okay? So I'm starting with pure nickel. I'm going to alloy it with tungsten, and then we're going to do Monte Carlo. So we'll move that tungsten around, we're going to query configuration space, and we're going to look at the distribution of solute as we equilibrate the system into something like an equilibrium state. And here's what we find. If you put tungsten into nickel, you load it up at a concentration of about 19%, for example, and you equilibrate, what you find is that it takes on a pattern where there are peaks and valleys, and every peak lines up with the position of a grain boundary in the structure, and every valley is the interior of a grain. And the reason it does that is because it is lowering the energy of the grain boundary. It's an energy lowering configurational swap. So starting from pure nickel, as you add more tungsten and equilibrate, you can lower the grain boundary energy, and you can lower it a lot. And in fact, you can get to within computational uncertainty of a 0 grain boundary energy if you dope those grain boundaries well enough, high enough. So what we can do with this kind of information from atomistic simulations is we can go back and we can do our very best to calibrate a regular solution model. And I'm interested in that because now this is where it starts to get interesting. What I find exciting about this is not just that there might be a stable grain size. I'm excited because that stable grain size might be tunable. So remember this curve here in red, that's the alloying effect, right? So that's the surfactancy effect. And whereas this blue curve is the grain boundary energy of pure nickel, that's my enemy and I can't do anything about that. It is what it is. This red curve is my curve, right? I put something in there to put that curve there, and so I can change what I put in there and I can move it around. For example, if you put in more solute, you shift that curve to the left, which means that I can control the resonance here where these curves cross. And in the end, I can hope to attain a master control like shown here. So this is the idea. As I add more solute to the system needs more grain boundaries in order to accommodate it in equilibrium. So the basic idea here, put in 5%, it decorates the boundaries. As I add more, the system wants to have finer grains in order to accommodate it. That's the basic idea. Now, can grain size be controlled thermodynamically? I find that an exciting idea. If you look at the way we usually process materials and get grain sizes, we're almost always getting whatever nature will give us, and we're trying to go faster and trick nature into giving us finer grain sizes. The idea here is that any grain size we want, we can dial it in and just get it through doping. And I find that interesting. So I had a PhD student. He was a very good PhD student, excellent. His name was Andy. And Andy had the task of trying to reduce this idea to practice. Okay. So I sent Andy off and I said, okay, this is easy. All we got to do is co-deposit nickel and tungsten. So go figure that out, okay? And Andy came back like literally one day later and he said, good news, boss. This is easy. Since the 1930s, people have figured out how to co-deposit nickel and tungsten. It's actually not that hard. You need two salts. You need a nickel salt and a tungsten salt. And those guys have very different reduction and oxidation potentials in solution. They're very, very different. So you got to put in some foo-foo dust here. You need complexing agents that in the bath will complex both of those atoms so that they can co-deposit at the same time. It's an induced co-deposition process. But sure enough, the recipe from the 30s, you know, someone uses it every few years, and it really works. And so here, I mixed up a beaker of goo, and it's green, it's beautiful, and I've electroplated things. And here they are. I already made samples, right? It took me one day. And that shows the power of hitting the library, by the way. And he said, look, there's actually some good news here. You can make really nice coatings this way. So, you know, they're as big as a penny, and I can grow them up to even a couple 100 micron thick. And they look pretty good. They look homogeneous. I'm really encouraged how quickly I was able to make these coatings. But there's some bad news here. So what's the bad news? And Andy says, well, I'm only able to make this one coating. It's got about 21, 22% tungsten in it. That's really all I can get. And you know, okay, I'm no expert on electrodeposition, Andy, but there's all these knobs you can turn. You can change the pH and the chemical loading, and you can change the temperature, and you can change the current you're using. Go change variables, right? Go do something. And like, it's not good enough to make one coating. We want to cover this entire range. And Andy said, I already tried those things. I already did 10 experiments. And in fact, in the literature, people have done that too. And here's the bad news. None of those work. There's a very narrow sweet spot for processing, and it's right here. And if I try to walk away from the sweet spot, I get coatings that look crummy, okay? So first of all, they might have you know, voids or crevices or cracks. And maybe you can see this, maybe you can't, but if you squint, you might see there's even macro segregation here, right? So we're not even properly forming an alloy. We're getting segregation as the thing is trying to grow. And so these are really crummy. The only way I get a good coating is to stay right here in this sweet spot.
You said one of the temptations was that by increasing the concentration of the dopant, you could move to lower grain sizes, but this curve seems to go in the opposite direction.
If I increase the concentration, I go to lower grain sizes. We're depositing way over on the right-hand side. It's a good question if I flip it. We'll come back to that.
Yeah, I was thinking hardness on the axis.
No, this is grain size. All right, so this is when a good PhD advisor makes their money, right? So Andy's got, you know, 80 years of literature saying that this is hard to do. No one's ever done it before. What do? I feel trapped. And what I did was what every good advisor does. Andy, go fix it. So Andy went into the lab, and Andy fixed it. And this was a very clever and inventive moment on Andy's part. And so I'm going to share with you what Andy did. I've made some cheesy schematics that illustrate it. This is the way Andy thought it through. He said, okay, look, I know I can make this one coating over here, this 21% tungsten coating, and I know exactly how to do it. I put the temperature at the right number and the pH at the right number, and I turn on the current at the right current density, and I deposit. And schematically, that might look something like this. Atoms are raining down on the surface, and they're getting incorporated, and I'm building an alloy. And you know, 20% of those, 2 out of 10, are tungsten, and they're getting incorporated. And Andy says, well, you know, what I really want is less tungsten incorporation. I really want to stop deposition, not so much as control it. And so here's what I'm going to do. I'm going to stay in the sweet spot. I'm going to keep all my processing parameters the same, and I'm going to turn on that current, and I'm going to deposit this coating, but I'm only going to do it for 20 milliseconds, which is just about how much time it takes to put down a monolayer, all right? Then what I'm going to do is instantaneously, thanks to power electronics, I'm going to flip the current on that thing. And instead of working in the potentials in the fluid, I'm going to work in the metal. And so for a very short spell, I'm going to actually etch. And I'm going to choose that etching potential such that tungsten is preferentially removed. And now, if I flip the current forward again and I put down another monolayer, that's going to get preferentially backfilled with nickel. And so he just runs this process, and you put in a pulsed waveform, and you run it for, you know, an hour or whatever. And at every layer, you do a little sculpting of the composition. You selectively strip out tungsten, and you backfill preferentially with nickel. And as the thing is growing, now you have a net effect of incorporating less tungsten. And this thing over-trivializes it because, of course, these atoms are all moving around, and they're assembling. And in fact, they assemble into nanocrystalline structures. And I'll show you that.
And how did he find 20 milliseconds? Is that in the literature?
No, you can calculate it. So you know the plating rate. In fact, it's a simple calculation. You know how many microns per hour, scale that down to monolayer thickness, and it's a 20 millisecond time.
This electrochemical trick is pretty well known in other systems, I'm sure.
Pulsing is definitely used. To use it to control grain size is not. And that's what I'm going to show you here. So what Andy showed you, what Andy figured out is that he could control the depth of these pulses and the shape of these waveforms, and he could walk around in composition space over almost the entire range. And because he never left the processing sweet spot, they all came out very, very clean, no cracks, no crevices, no voids, so beautiful material. And sure enough, we're hoping that we can control grain size in this way. When you actually make a bunch of these films and you look at them, their grain sizes turn out to be remarkably in line with what we were hoping to see. And so these, I think, are X-ray data. If you go do the TEM, you can see that with a little bit of tungsten, you get coarser grains. When you get to 10% tungsten, you're down to the 20 nanometer range and the 10 nanometer range. And if you go up here to where the sweet spot is for DC plating, you end up with something that has been interpreted as amorphous in the literature, but it's not amorphous. It's very, very fine single-digit nanometer grains throughout the entire bulk of the sample. So this thing is looking really good, right? So Andy came up with a technique to walk around. We got a lot of samples that sort of look like thermodynamics is at play in controlling their grain size, so hooray for Gibbs. In fact, I named my dog after Gibbs. So Gibbs is a purebred poodle, and he's not quite big enough to be a standard poodle. I call him a substandard poodle. And it's really useful to name your dog Gibbs because you think of thermo constantly, right? It's always right in your face. So I recommend that. All right, so the whole idea here was we wanted to stabilize the structure. So far I've shown you I can control grain size. My premise is that all that grain boundary segregation is going to help me stabilize the structure. But actually, I haven't even shown you grain boundary segregation yet. So I've got some stones still to turn over before you believe me. So let's go back, and I'm asserting that this trend is associated with segregation of tungsten at the grain boundaries. And one thing we do know is that these are all solid solutions. They're all FCC. There's no other phases that we're finding in there. But we need to have evidence that there's segregation at the grain boundaries. And so this is another classic Andy moment. You know, Andy, good job, but you can't graduate until you prove there's segregation at the grain boundaries. And Andy says, this seems hard. Let's say I work on the finest grain size and it's 3 nanometers. How am I going to go image that? I'm not a microscopist. Maybe someone could do that, but that seems hard. And by the way, the simulations kind of told me that I'm going to get a very subtle signature. The boundaries are going to be enriched by a few %. So really small length scales, really subtle chemical signatures. I don't know, boss. I don't think we're going to be able to do this. And you know what I said. Fix it. And Andy fixed it. So Andy went to Oak Ridge National Laboratory where they have an atom probe. You guys have an atom probe here? No? I don't have one either. If you don't know what an atom probe is, it's a very cool instrument. What it basically does is it lets you take your specimen, and what you do is you sort of electrochemically whittle your specimen into a little needle. And so in our case, we take these foils of nickel tungsten, we turn them into little needles. You put the needle into a vacuum chamber adjacent an electrode, and by pulsing a very large voltage between those guys, you can get a field effect emission of one atom flying off the tip, right? So you pulse the voltage and you send an atom flying, and you detect how long it took to reach a detector and where it hit that detector, and you can actually back out its position and its chemistry when it started. Right? And if you do that once, I guess it's pretty boring because one atom goes. But if you do that 1 million or 10 million or 50 million times, you can actually deconstruct your sample one atom at a time and reconstruct in the computer to within some uncertainty the position of every atom and its chemical identity. And so here is one of our samples. This is nickel tungsten. It's a needle shape. We're ablating it this away. And we've reconstructed it in the computer. And do you see grain boundary segregation? Yeah, good answer. Yes, you do. It is in there. But you actually can't see it. And so one of the problems with atom probe tomography is that you actually don't see grains. It's not so good at actually seeing crystals and orientations. It just sees chemical signals. And there's enough noise in the position data that you don't see where the grains are. So this is an opportunity. We now have experimental information, and we have simulations at exactly the same length scale, right, on exactly the same phenomena. What we're going to do is we're going to use the simulation data where we have equilibrated it and we know there's grain boundary segregation. We're going to use that to teach us how to interpret the experimental results. So here's what we do. We take these needles, we characterize them in the TEM, we measure their grain size through X-ray, through TEM. Then we get the chemical data in the atom probe. Then we go and we build the simulation at the same grain size, 3 nanometers, and the same composition, and we equilibrate it. And now we pretend for a moment that we don't know where the grain boundaries are in the simulation. So let's do some kind of statistical analysis of this equilibrated structure and look for segregation without knowing where the grain boundaries are. For example, one of the things you can do is look at the two-body correlation, the pair correlation function between tungsten atoms, right? If all the tungsten atoms are preferentially distributed on the outside of the grains, you will see something like this, where there is a primary maximum that is at the grain size. That's the, if you will, it's the wavelength of tungsten in the specimen, and it matches the grain size. And we know that's because, indeed, in the simulation, it is segregated at the boundaries. Well, now we can go do the same thing. We've got all this position data over here, and so it is very heartening when, in the experiment, we get the same wavelength at 3 nanometers. Are we starting to believe it, that there's grain boundary segregation? Maybe. It gets more convincing if you do it again. Do it at 10 nanometers and at 20 nanometers, and Andy can give you all those grain sizes because he figured out how to do it, right? And when you run those guys and you get back out chemical signals at 9 nanometers and 17, now you start to really believe that no matter what length scale we put in, we're seeing tungsten distributed at the same length scale as the grain size. If you have a really well equilibrated sample, sometimes, and if the grain size is lucky, big enough, then you get lucky, and I can peel out little portions like this one and just show you the tungsten atoms, and if you cross your eyes, you will see a grain structure here, and indeed, you can go in and you can mill across individual boundaries in the computer and convince yourself that, in fact, when you cross a grain boundary, you get a pulse of tungsten when you go across those guys. So with this, I let Andy graduate. Because he had validated the basic idea. We're going to electrodeposit these things, we're going to control their composition, and the boundaries in the as-deposited condition are decorated with tungsten. Now, if everything holds together, that should help stabilize this structure, right? So you will recall the work of Hibbard on pure nickel, where in seconds or days at 400 degrees C, we watched the grain size explode from nano to micro. If we run the same essential experiment now on nickel with tungsten in it, the grain size going in is about 12 nanometers. We can heat it to, even a little higher than Hibbard, and we can heat it for days. And the grain size coming out is within experimental error of what went in. So for practical purposes, these things are remarkably stable. More on that tomorrow and the day following. So we have here, in principle, something that looks pretty good. We're electrodepositing nanocrystalline structures. Nickel turns out to be way easier to electrodeposit than chrome. And so a lot of the challenges associated with chrome turn out to be much better just because you're using a nickel process. We didn't design that, we just got lucky. And of course, the environmental hazard is now dramatically lower because neither the tungsten salt nor the nickel salt or the ions associated with those create any environmental hazard on the scale of chromium. But this was not the problem. So we have a competing process. The question is, can we deliver the performance? So let's get out of the lab now. We got our PhD. Let's go get some field data, all right? Let's start, first of all, with hardness. So here's the Hall-Petch curve for nickel. Can we repeat this with nickel tungsten? We can. Here are the nickel tungsten data. Any grain size you want, Andy can deliver it by controlling the waveform. And so you can walk up and down, and in fact, you can hit very high hardness levels, akin to what you would get in chromium. So that's good. I'm going to talk to you about where, but before I do, I have one more trick up my sleeve. Or maybe I should say Andy has one more trick up his sleeve. So there's a lot of flexibility here. I can control the grain size, and I told you how we do it, right? We do it by changing the shape of this waveform as we're growing the coating. So we don't have to do that necessarily from one sample to the next. We can do it on the fly as the coating is growing. So here's a schematic. I'm about to grow a coating for you, so please appreciate this hard-won animation. This is the substrate, and I just electroplated 20 microns of a coating. And I've used a certain waveform that delivers 20% tungsten and an associated grain size that goes with it. And now, on the fly, I can change that input, and I can render a second layer of coating, which is designed to have 15% tungsten and a different grain size. And of course, I can do that again. Here's a third layer, and again, and again, and again, and again, and again. So I can make materials that have all kinds of different grain sizes through the thickness. I can do functional grading, I can do Neapolitan structures, layered structures, any coating you want. Grain size is no longer a variable, it's now it's a state variable, right? It's a position-dependent variable. And that turns out to be remarkably useful, and I'll talk more about this tomorrow, but when it comes to wear is not just about being hard, it's about distributing damage. And so if you can control many different layers, you can control the way damage evolves. And in fact, we've been able to make materials that are not only as hard as chrome, but in a wear situation, they beat the pants off of chrome. So I'm going to show you an example. So this is my commercialization partner for all of this work. So Extalic is in Marlborough, and they distribute the chemistry and the technology to plate this particular alloy. And in the spirit with which I started on working on totally unsexy and mundane products, I submit to your consideration this happy fellow here. This is what they call a gravure printing wheel. Okay, so this thing is it's about yay big, and it has embossed lettering on the outside of it, and it is going to be used to print some very unexciting information by putting ink on one side and transferring it in a rotating mode against a medium here. This guy is used to print the lettering on the side of electrical cables. So every electrical cable around us has this on it. I'm looking at it right here. This is the guy that does the work of putting those letters on. So this product is a classic example of what we use hard chromium for, right? So you never see this, but it touches your life in a million ways. And the way they use chrome here is that they make this wheel, they emboss the letters, and then they chrome it to make them hard, because they're going to spin very, very fast, and they're going to print 20 miles of this wire. And it's going to be smacking and wearing, and gradually you beat those letters down until this is insufficiently legible. And that's the failure mechanism of this guy. Well, the guys at Extalic, they took this toolkit, the nickel tungsten, the nanocrystalline material, the layering technology, and they empirically designed a coating for this application, and they delivered a product that prints 10 times as much without needing to be replaced or changed. So not only is this greener, it's a green alternative to chrome, but it is a dramatic premium in terms of the lifetime of the component. Corrosion. Corrosion is a complicated topic, and at the risk of trivializing it, I'm going to just tell you that when it comes to layers, there's a lot of tricks you can play with corrosion, and tomorrow I'll talk more about how you design something with layers to help with corrosion. But you can actually find a lot of situations where in corrosion you can do much, much better than a monolithic coating. And if you can do corrosion, then that means you're better at luster as well. And so I'm going to show you what I think is still, we did this almost 10 years ago, but I still think this is the largest monolithic deployment of a nanocrystalline material out there. And so this is the electroplating tank in which this thing is produced. And for scale, you're standing at a railing, right? So this thing is, you don't have a great scale here. It's about as big as a hot tub, I guess. Don't swim in it, right? So here it is. The old Navy guy gives you the scale a little bit better. I have no idea who this is, but so this guy is hoisting up the product here that is coated in nanocrystalline tungsten, nickel tungsten, sorry. Does anyone recognize that component? No? It's a totally unsexy, yes, I heard it. Someone got it. That is a Class 8 semi-truck bumper. Okay. So this is a very interesting application for chromium coatings. These are steel substrates. You coat them with chrome because these trucks are going to see incredible circumstances. In 1 year, they're expected to go 100,000 miles. And you guys are Midwesterners, you get this, right? So am I, by the way. These things go incredible distances, and they see every environment, right? So it's going to start up in New England full of blueberries, and it's going to hit snow and salt and probably a moose, and then it's going to come down through here, and we're going to hit, what, like a beaver? I don't know, whatever. And then it's going to go to the desert, and it's going to get hit with rocks and tumbleweed, and so it's going to get impacted a lot. There's a heavy mechanical component to this, and there's a heavy corrosion component, and it still has to look pretty. Right? So the warranty on a chrome bumper is 1 year, 100,000 miles. The guys at Extalic took this application, and they engineered an 11-layer stack, 11 different grain sizes, empirically tuned to resist impact damage and to help protect the substrate against corrosion. And their product rolled out and was fielded on fleets of trucks in 2008, rolling all across North America with double the warranty. So, I've come to the end of my first story. What I hope that I have done with this story is shown you, first of all, the power of working with great people. So you've already met Andy. There was another student involved in this at MIT, and a great team at Extalic that did the commercialization work. Mike Miller at Oak Ridge helped us with the atom probe. But if there's any sort of takeaway here, it's that you can start in the lab and do some very basic science. You can do simulations, you can bend equations, and all of that can contribute to the development of new processing science, the production of new materials, and indeed to engineering applications at the end of the day. The important concept from today that will recur throughout the week is this idea of segregating things to grain boundaries in order to stabilize nanostructure and enable engineering applications. And so if you are able to join tomorrow and Thursday, I'll tell you the next segment of the story. And thank you for your attention.
I'm sure there'll be lots of questions. Professor Ernst.
I know it's all my fault because the way I advise you to give these presentations, but I think you gave us a very simple picture of what the tungsten does. You said it lowers the grain boundary energy. Is this really true? I'm thinking if you just had the grain boundary and you bring in tungsten from outside, would the grain boundary energy really go down? Or is it such that having the tungsten in the grain boundary is energetically more favorable than having it built in the grain crystal structure? And then also, the tungsten could in principle actually change the nature of the grain boundaries, and it could impact the texture of the material that forms. And that could also reflect back on its mechanical properties. Do you have any knowledge about these questions?
I do. So you are correct that I have swept a lot of details under the rug, and I'm happy to sort of dig them out. So first of all, on the issue of texture, so all of these materials are texture-free, and so we have measured them in every possible way, and no matter what grain size I'm talking about, they come out remarkably isotropically oriented, remarkably untextured. And it's something associated with scale. When the grains are large, you get more epitaxy. When you get down to the 100 nanometer level and below, they become equiaxed. You don't see elongated grains any longer, and the texture becomes quite random. So I don't think it changes the texture. It does change the grain boundary energy. And the grain boundary energy, you correctly identified it in the second way you described it, the sort of Gibbsian way, is relative to dissolving it in the bulk, right? So it lowers, So that's the correct calculation. That's the calculation that we do. So it does lower the defect energy relative to the competing solid solution. And so relative to grain growth, it's a more stable configuration in this way. Does it change the structure of the boundary? It does. Almost certainly it changes the details of the crystallography of the interface and how disordered it is, and I haven't studied any of that. I also treat every boundary as kind of being equal when they're clearly not, right? So a lot of details. Yep.
Calls for bicrystal studies.
Yep. Indeed it does. Yeah. A lot of details. Good questions.
Other questions? Student questions? Conrad?
Yes, so you talked about the nanostructure of this nickel as just in terms of the Hall patch strengthening there. But compared to the chrome, which had a much bigger crystal structure, are there any other side effects, diffusion through grain boundaries, substrate interactions? On that note, you haven't talked at all about the substrate these electrodeposition occurs on. Can this occur on any substrate, or are there specific substrates that this crystal coating is better on?
To first order, the substrate doesn't matter, I would say. So provided that it is electrically conductive, you can plate upon it. There is a lot of art in how to do it well, right? So things that are surfaces that are oxidized or scummy in some way, you have to do a lot of preparation in order to render a surface appropriate for electroplating. I think right at that interface there probably are epitaxial things that happen, but by the time you get to the thickness we're talking about here, it is not typically relevant, so I haven't looked at it at all. Was there something else that I forgot in your question?
I think that covered the major points.
Professor Lagerlof.
So as you electroplate, you're consuming certain species. Do you supply them continuously or?
Yeah, typically in the industry, you would supply those continuously, either through a dissolvable anode or through a dosing pump that would be calibrated to the current flow. These baths run perpetually, right? So in a beaker in a lab, you run into depletion problems, but in the industry, it's the chemistry of the bath is held constant for years.
There are a number of student questions. Let's get to some of those and then Gerhard will come back. Ben? And then
How are you defining, or what metric do you use for the simulations that you run to define equilibration of when it's settled down enough for you to take a snapshot in time and make these measurements?
So it's an internal energy measurement. So at every given moment, you sum up the energy of all those atoms, and then as you're swapping them around and exploring configuration space, it comes down sort of monotonically, and at some point it stops changing, and it's sort of a judgment call of when you've reached that asymptote. And of course, that may or may not be as low an energy state as is possible, but it is some approximation of an equilibrium. So that's how it's done.
question right here.
So you mentioned that alum constant into nickel can decrease the nickel particle, nickel grain size. So the grain boundaries can accommodate more constant items. So when you alloy more constant than you already have, will it becoming amorphous? The structure will be more hardened and will be more corrosion resistant.
So your question is deeply philosophical. I personally sort of have the view that if you get heavily doped enough, nickel tungsten is in principle, I think, an amorphous forming system. So if you have above 25–30% tungsten in there, I think it can sustain what we would call an amorphous structure. So my view has always been that, yes, this is a smooth transition to something that is amorphous-like, although John will tell you that definition of amorphous is somewhat in the eye of the beholder. So when the grain size goes from 3 to 2 to 1, is it still a grain? We're right in this gray, fuzzy territory. What I can tell you, though, is that the properties seamlessly merge. So if you just detach yourself from structure and you measure properties, things like strength, rate dependence, pressure dependence, all of our favorite things, you can watch them go crystal-like to glass-like as you go across that transition. And so amorphous is not harder. In fact, if you go, I didn't show it because I didn't want to open this can of worms, but that peak in hardness, it comes back down. The Hall patch effect breaks down unequivocally, and the properties start to look very amorphous-like. It starts to shear band and look like a glass when you deform it. It becomes pressure sensitive. So a whole bunch of physics sort of shift in that range. And so it is, to first order, it is amorphous-like, I would say, yeah.
How do you measure the tungsten wavelength, as you call it, in reality, in real sample, in TEM images that you show?
It's not in TEM, it's atom probe, right? So the atom probe spits out a giant list of every atom, its position, X, Y, Z, and its composition. And so if you have all that data, you strip out all the nickel, you have all the tungsten positions, and you just do a two-pair correlation function on that data. Boom, that's what it is. Yeah.
We'll mix in a Professor Welch.
Yes, the system of tungsten nickel is known in the tungsten metallurgy field as one where nickel segregates heavily in tungsten because tungsten is very low solubility grain. And when it segregates the grain boundaries, it does the opposite. It causes exaggerated grain growth, just the opposite of.
And rapid sintering too, right? Yeah. Activated sintering, right?
Yes, that's exactly. So how do you compare this to yours?
Well, so I think the sort of cop-out answer is that this is the opposite side of the phase diagram, and it's a different structure, it's a different base structure, and so I don't think that you can just, because the elements are the same, sort of look for.
Right. We also have another temperature regime.
The homologous temperature is completely different, right? So I'm on the nickel-rich side where tungsten is the slow diffuser, and yeah, so I don't think I have a smarter answer than that, but I just don't think I'm looking for symmetry on those two sides of the phase diagram.
So you said one of the disadvantages of chrome coatings with inefficiency. Is
Yeah.
it in terms of how much energy you need to put
Yeah.
down a given?
Current inefficiency, yeah, and there are other inefficiencies that are production related, but it is current inefficient as well.
Okay, so you're green in another aspect in the lower embodied energy of your coatings than of.
Possibly. I've never done the calculation, but it's possible.
Yeah, we have to take other things into account.
Yeah.
But in the manufacturing at least.
It's a good idea.
less energy.
Yeah, I've never calculated it out.
See, there were some more student questions in the back, first there and then that.
So speaking more to the engineering side, tungsten's much more expensive than chromium. So like, does the lifetime performance on the parts outweigh the costs?
Great question. So the success of the things that I've shown you, these are all technical successes. They are of mixed market success, and there are many more like it. So this is not a general chrome replacement for the reason that you suggest. There are many market niches where the selling it on an increased lifetime doesn't work, right? Because the person buying doesn't see the value those many years out. So there are a lot of applications that have died on the vine because this is definitely more expensive than chromium. It's very dependent on the application. In the case of the bumpers, if I remember correctly, they were about a 5 to 10% premium, cost premium, but a doubling in the lifetime. And so that, in some economies and to some customers, can sell, but to others it can't.
Matt?
I was going to ask a very similar question.
Okay. Professor Carter?
Oh, have you thought about doing a similar potential switch for zinc coatings? You see zinc coatings for corrosion resistance, and nickel and tungsten wouldn't be considered lightweight elements. So you could see some lightweighting issues. Have you played with the zinc plating at all?
So I have two answers to that. First of all, lightweighting, it's remarkable how little coatings matter in the lightweighting proposition in the final analysis. So it's never come up as a real issue. Zinc is, so these tend to be used for barrier type corrosion protection, right? So and it's about having a coherent coating that sort of keeps the substrate from ever seeing corrosion media. Zinc is the opposite, right? It's a galvanic sacrificial coating. And I have touched it slightly, and tomorrow I'm going to talk about galvanic corrosion coatings based on this kind of idea.
Right here.
Is there a thinness limit to the alternating layer structure?
Oh, good question. I have no idea. Yeah, I've never pushed it. Presumably there must be. I mean, if the layer is smaller than the grain that you're dialing in, yeah, good question. Don't know.
So I have a quick question about the different layers. So there's a different composition in terms of the amount of tungsten you have. Do you see any of the layers bleed into each other? Is there any diffusion happening? And how stable are the layers when you layer them on top of each other?
Another great question. I've always wanted to study that and never found the funding and or time. Yeah, so I think it's a question. So in an ideal thermodynamic model, the way I've described it, I'm changing the composition and the grain size together in such a way that the chemical potential is kind of constant across those layers. So would they diffuse? I don't know. If they interdiffuse, the grain size would have to change at the same time. It's sufficiently complicated that I'm not even sure what hypothesis to offer, what would happen, and I've never been able to go heat them up and study it in any detail, so I'm sorry. Yeah.
Other questions? Comment?
Yeah, so on the note of the deposition, it seems like this layering process is very current dependent. You're exercising very high control of the electrical current to create this layer effect. Now, when I'm talking about a large electrochemical bath for the bumper that you've shown, I expect there to be a large amount of variation in terms of what each individual surface sees, just in terms of distance from the electrode. Has this been an issue in large-scale manufacturing, and is that what you can address?
It's a great question. So the good news is that this is a known area of art in the world of electroplating. When you're plating a complex shape, there are artisans and scientists who do nothing but sculpt field lines so as to try to get uniform coverage on complicated parts. So you have lots of different electrodes, you have shields, you have you'll occasionally put in sacrificial cathodes. You plate on stuff that you don't really care about just to draw field lines. And so there are people that know how to do that. And the good news is that when you apply the pulse waveforms and so on to first order, the standard art just kind of translate and it works. So on that bumper, early on when we started plating those things, you got to carve it up and make sure the grain size distribution is the same all over that thing. And it is. And it's, in some sense, lucky. Yeah.
So you don't lose any throwing power by the tungsten addition to the
No, and to the contrary, the pulsing tends to help with throwing power because pulsing does, a more common use of pulsing is to increase throwing power because you deplete off of the regions of high field preferentially, and then you deposit on regions that are less affected by field. So you get a slight benefit in throwing power. It does slow down your plating because you're not just straight out plating, you're stripping a little bit all the time. So it's a little slower, but you do get better throw.
Are there any other questions? A lot.
I have a quick question. So you mentioned that tungsten, as we increase tungsten, the grain size will get smaller and smaller till it reaches automotive space. My question is, does it happen with increasing tungsten forming separate phase, like enriched in tungsten, and how that affect the properties?
I hope that you will come to the next two lectures because indeed, so your question is prescient. So the primary instability in these materials is the second phase wants to pop out, right? So tungsten wants to go to the grain boundary. That's an enthalpic ordering proposition, right? It wants to go to the grain boundary because it can achieve a degree of chemical order that it cannot in the bulk. And the competing state for nickel tungsten is there's an intermetallic, nickel 4 tungsten, a bulk ordered state. And so you're exactly right. If I heat this up hot enough, bam, nickel 4 tungsten pops out before the grains grow. The instability is the second phase, and then the grains grow like crazy. Yeah, so good question. And in fact, that's what I will talk about. I think on Thursday, I'm going to talk about how do you deal with the second phase issue.
Well, it looks like we may have exhausted everyone. This is exactly the purpose of this kind of seminar, so we appreciate the student questions. Keep them coming tomorrow. So we want to thank Professor Schuh for giving an excellent first lecture of 3.